Okay guys, welcome along to this video. Today I'm going to be talking about why I developed PetThermoTools to start with and some of the main aims that we had in developing PetThermoTools. So this has really been a collaborative effort from myself, Penny Weezer, Paula Antoshetskyna down at Caltech, and Nicholas Reel, who's the developer of Mage Mint, which I'll talk about in a bit more in a little bit of time. But really from developing PetThermoTools, there was one main motivation for it, and that's that thermodynamic modeling has been like a really influential part of igneous spectrology and volcanology for the last few decades, right? There's various different studies that have used thermodynamic models for various different purposes in igneous spectrology. These could be things such as eruption triggering mechanisms. A study from a couple of years ago came out doing just that. There have also been studies that have attempted to use thermodynamic models, melt specifically, to understand the pressure of magmatic systems. Once again, a study that came out doing this a couple of years ago, looking at lunar basalts, shown here. And melts and thermodynamic models more broadly have been used in a wide range of different things. There's an example I'm going to show you here from some of my work, where we use some melts calculations to look into what happens to the porosity of crystal mush systems as they react with percolating melt phases. And so my point here is melts and thermodynamic models more broadly are used for a wide range of different purposes within igneous spectrology and volcanology. So the question is, why do we need PetThermoTools, right? There are many different ways you can run melts calculations. There are also many different ways you can run calculations with the Green et al. 2025 or Holland thermodynamic models. Okay, so why did we need, or why in my view did we need PetThermoTools, and why did I develop it? Well, when I looked at the available kind of options for running melts calculations, this is kind of how I put them on this graph. This kind of whether you have great flexibility in what calculations you run, or at the bottom you might have very limited number of options. Yes, you could do crystallization or melting or a simple decompression calculation, but you can't do much more beyond that. And then on the x-axis, I'm showing how easy it is to use. How easy is it for someone with no real coding background or knowledge to come along and actually use these different tools, right? So down on the bottom right down here, you have things like the original Rhyolite Melts GUI, or otherwise Easy Melts. There's another GUI that has been developed as well. These things are very easy to use. You plug in a sequence of numbers, you hit run, it runs a crystallization or melting calculation, and then it prints out some results, and you're able to use those and plot them up separately in order to investigate your particular system. Okay, so it's very easy to use. Anyone can come along and do it. You could use it with an undergraduate class. People can plug in some numbers and run a crystallization model and see what happens to your melt compositions. It's very useful tools. The problem is, if you wanted to say run 1,000 calculations, that would take a long amount of time. You'd have to manually type in 1,000 different compositions, load in your pressure and temperature requirements each time, hit run each time, take that material elsewhere so you can plot it up later, etc. It takes a large amount of time. And this is one of the reasons why a lot of people that use melts very regularly end up working with either alpha melts or thermo engine. And these kind of more advanced systems allow that greater flexibility. You can loop through calculations and do hundreds of them. You can, rather than working just pressure temperature path, you could use enthalpy to define your path and work out that kind of how crystallization proceeds if you go down set amounts of enthalpy rather than temperature at each step. So there's a much more flexibility in what models you can run here. The problem is that if you're new to this kind of stuff, they're, to be completely honest, not very easy to kind of get started with. There's a large learning curve associated with that initial step of getting in towards these different models, or these different software systems. And that's kind of what I wanted to address with PetThermoTools. I wanted to create something that would still be relatively easy to use, but would still provide quite a lot of flexibility within the types of calculations that are available and things that you can do with those calculations. Okay. And so the idea for PetThermoTools was to take the amazing Alpha Melts with Python package that has been developed by Paula Antoshetskyna and provide wrappers to that. Provide functions that wrap the Alpha Melts with Python underlying source code, and it minimizes the amount of work the user actually has to do in order to run typical thermodynamic calculations. Obviously, there's some penalty for this. You might not be able to do everything you'll be able to do with Alpha Melts or Python or Thermo Engine, but for the vast majority of thermodynamic calculations, you should now be able to do them within PetThermoTools far easier than you would be able to do in Alpha Melts with Python, especially if you don't have any prior coding background. And so the main aim of PetThermoTools was really to take alpha melts, and specifically we're talking about the Python versions of alpha melts. You can see one of the most recent releases shown down here, the 2.3.1. We were trying to take this alpha melts for Python package, and really what we wanted to do is kind of take this excellent bit of code from Paula and just kind of wrap it up so that it can minimize how much user input is actually required in order to do typical or common thermodynamic calculations. Okay. Making it as easy for the user as possible to run their code, meaning it's easy for people to use even have no prior coding experience, and potentially even very easy to use in undergraduate classes. I've used this in undergraduate classes. And so I'm just going to show one example here. This is an example of a crystallization calculation. So we're just going to say PTT stands for PetThermoTools. Isobaric crystallization is the function. I'm just going to specify which thermodynamic model we want, give it a starting composition, tell it to start at a liquidus. An array of pressures actually means it's going to run 4 different calculations. What temperature we want to end at, temperature steps, and how big are the temperature step going to be during this crystallization calculation. Information about the oxygen fugacity. Information about whether we want to fractionate solids and fluids from the systems. And in this case, we're actually going to specify an initial water and CO2 content for the system separate from our bulk. Okay. This calculation is going to run. It's going to run 4 different crystallization calculations on my MacBook. This will take around 3 seconds. And then after this, we're going to use the Harker function that's also part of PetThermoTools in order to plot up this data. So we're going to plot our results, and we're going to plot it against some melt inclusion and matrix glass data that I've separately loaded in to my Python environment. Okay. So just from those 2 functions, nothing else other than loading in those 2 data files for melt inclusions and matrix glasses, we're able to produce results such as this. We can simulate and look at the kind of compositions predicted by 4 different crystallization calculations at different pressures and compare them to natural data. In this case, this is data from the Galapagos archipelago. This is melt inclusion and matrix glass data from Isla Floriana. Okay. So that's just an idea of what we were trying to do. We're trying to take alpha melts for Python, which is an excellent package, but provide it in a way that anyone can come along and use it, regardless of their prior coding experience. And so to kind of just demonstrate that again, let's just run through another example. So on the right here, we're going to essentially be producing this graph on the right. This is a graph produced by adiabatic decompression melting. So you can see as you go to lower pressure, the liquid component in this mass fraction graph is going to increase. Okay. Now, when running this, the first thing to do is to install the package. There are other videos that are going to be put up about installation and several example videos talking through different types of calculations as well. So I'm going to go through this quite quickly. So you install the package, restart the kernel. Once that's been done, you then need to import PetThermoTools into your Python environment. So we typically use the letters PTT for PetThermoTools here. Optionally, you might also have to add or append the path to the alpha melts for Python source files in here. Don't worry too much about this now. Go and see the installation videos if you want to see more information on this. For most users, this isn't going to be necessary. The installation steps will actually allow you to add these files to your Python path permanently. But in some cases, when that isn't possible, typically if you don't have administrative privileges on your machine, you'll have to append them in the manner shown here. Okay. So mainly the main thing to do is import PetThermoTools as PTT, and then nothing else on there. We can then run a function. So ptt.adiabatic decompression melting. Once again, specify our thermodynamic model. And in this case, we're going to specify our bulk as KLB1. PetThermoTools has a couple of saved bulk compositions. The alerts are like KLB1 is one of them. Other than this, we're going to specify the system conditions. So in this case, the potential temperature, the starting pressure, end pressure, and the pressure step throughout the calculations. That calculation is going to run. Once again, it takes a few seconds on my computer. And we can then take this results variable and pass it into our phase plot function, specify we want pressure on the y-axis, and that's all you need to do in order to produce this graph on the right-hand side. Okay, just 2 simple lines, 2 simple functions, 2 simple lines of code. That's all you need to do in order to run an adiabatic decompression melting model and examine the results. And in fact, we've already managed to develop a large number of different functions that can be used with PetThermoTools. Okay. So they're kind of shown here, and on the read the docs page, we're going to update this figure as we move forward. So we're continuously updating which functions are available And we're kind of expanding the functionality both within functions, so adding more features into functions that will give you more flexibility in your calculations, but also expanding the number of calculations that are available. For example, one of the things I'm currently working on is expanding the adiabatic decompression melting function so we can simulate two different sources, so a multi-lithology mantle, and allow that adiabatic decompression melting to occur, assuming these systems are thermally in equilibrium but chemically isolated. Okay, so that was one of the main aims. The main aim is to provide a wrapper to the alpha melts functions so that it's easier for people to use it. Okay. The actual initial reason why I went along and started developing PetThermoTools back in mid-2022, I believe it was actually because I was trying to use alpha melts with Python for some of my own research. And I came across one of the really unfortunate kind of features of alpha melts with Python in that if a failure occurs in alpha melts with Python, you can't actually reload the melts library in your Python environment. You get this message, melts library already initialized, could not reinitialize melts library. And basically what this means is that if your melts run on the previous calculation had failed, you would not be able to reload melts. Okay, so that failed calculation basically stuck and it stops any further calculations from taking place. And this basically means that if you're running, let's say you're running hundreds of calculations, what actually happens is you might get to calculation number 2, calculation fails, you have to restart your kernel and try again. Okay, reload all the parameters, set the conditions running again. And the reason why I developed PetThermoTools was to try and get around this problem. Okay. And so this is how we kind of did it. So when you run most melts calculations, say you're running multiple melts calculations, whether this is through alpha melts, thermo engine, melts for Excel, it doesn't matter. What's typically going to happen is you're going to set up your calculation. You're going to give it a composition, a pressure, a temperature, and you're going to ask it to run potentially down temperature, crystallizing as it goes. Okay. It's going to do this for composition number 1. It will do that first run. Once that's finished, it will then go and do the second run that you asked it to do. Once that's finished, do run 3, run 4, etc. In this case, let's say I give it 4 calculations, as I did for the crystallization calculation I showed near the start of this video. Once all those calculations are done, we'll then present the results. You can plot these up and examine your model results. Okay. The problem that I've just described is if an issue happens on run number 2, so there's a quadratic minimization failure and melts and no solution is returned at one particular step of the model, that calculation will fail. The problem initially is that with the way alpha melts with Python initially worked, is that would mean run 3 and run 4 would also fail to run. So you would potentially get results from run 1 depending on how you set up your code, but that's all you would get. So say you had set this up to run overnight, you set 1,000 calculations sequenced up on your computer to run overnight. You went away, went out to have dinner or something, you came back and 2 calculations run and that was it. Okay. That's essentially the situation I found myself in frequently when trying to do some of this work. And so what I did with PetThermoTools instead is I made use of parallel processing. And so essentially what's going to happen here is we're going to set the calculation up in a very similar way. But rather than running these different models sequentially, what's going to happen is you're going to take a sequence of models and send them into different what are known as child processes. Okay? So you're going to send the information off to a child process, and in that child process, each child process is going to run one of the different models that I've requested. Okay? So once again, if I've said I want 4 different thermodynamic models to be run, it's going to initialize 4 new processes, and within each of those processes, a different model is going to take place, and these are going to run in parallel with each other. If you have more than 8 models that you're trying to run, most laptops will handle around 8 models at once. If you have more than 8 models and you're using a typical laptop, it will do a sequence of 8, wait for those to finish, and then we'll load a second sequence of 8 after them. Okay. The main importance here, though, is that because these are running in separate processes, they're not running within the main Python process. If run 2 once again fails, that doesn't really matter. Run 3 and run 4 are still going to occur. Run 1 is still going to occur. And the results from those 3 other models are going to be returned. And in fact, with the way the code is set up, the results from run 2 up until the point of failure will be returned as well. And this means that that failure doesn't affect anything happening in the main Python process. It won't stop you doing any further melts calculations. So if you wanted to run hundreds or thousands of calculations, you can do it. Some of them may fail. That's part of thermodynamic modeling in many ways. But the rest of them will continue and will run correctly, and you will get results. That's one of the main advantages of PetThermoTools, is protecting that main process. I mean, that any calculation failures that do occur, they don't influence what's happening within the other calculations. This means that in this case, rather than only getting results from run 1, I can get results from run 1, 3, and 4, and potentially results from run 2 up until that point of failure. Okay. And a kind of almost side effect of this is it actually also speeds up the calculations. Because we're running these calculations in parallel, what actually is happening is we're going to split the thermodynamic calculations across your computer's CPU, across the different processors that are available on your computer's CPU. And this means that we can actually maximize the CPU of your particular computer. How many processes are initialized at one time will be automatically determined based on the specifications of your machine. So what happens is we'll actually split the calculations across different child processes, run them simultaneously, and ultimately what this does, depending on the machine, this can lead from anywhere from a 2 to 4 times speed improvement if you're doing 8 calculations at a time on typical kind of personal laptop machines. So let's say you were doing 1,000 crystallization models, as I've mentioned many times. On my MacBook at least, this would maybe take 1 or 2 hours kind of thing. Nowadays, I can usually do that in somewhere between 15 to 30 minutes. Okay. So it's a significant increase in the speed. I'm not saying at any point that this is necessarily like incredibly fast and you can suddenly start to include melt simulations in with like geodynamic models or anything like this. It still is taking a reasonable amount of time to run these calculations, but you can, especially when running multiple large amounts of calculations, the total time required for those calculations will significantly reduce, especially because the setup is also much easier now. Okay. All right, on to the third point of why I set up PetThermoTools. So I've spoken quite a lot about alpha melts. Okay? It's a brilliant bit of software that allows you access to the kind of melts thermodynamic models. Okay? And the initial PetThermoTools version just accessed alpha melts. Okay? It ran calculations through alpha melts, so it allowed you to model things with P melts or the rhyolite melts thermodynamic models. When I started developing this, a new bit of software suddenly appeared, and this was known as MageMin. Okay, some of you may have heard of this already. There's an excellent bit of software written by Nicholas Reel. It is written in C but has wrappers in Julia. And basically this software is similar to alpha melts. It's a Gibbs free energy minimization software. So it finds the minimum Gibbs free energy of the system to understand what is the equilibrium point in that system for that composition, pressure, temperature, conditions. Okay. The important thing with MageMin is this doesn't actually work with the melts thermodynamic models. Instead, it uses a range of other thermodynamic models, many of which have been used to some extent in igneous petrology or volcanology. One of the two of the major ones that are currently used are the Green et al. 2025 thermodynamic model, which is an update from Tim Holland's 2018 thermodynamic model, and Owen Weller in 2024 published another thermodynamic model based off similar things that is specifically designed for alkaline igneous systems. So those two models, the Green et al. 2025 and the Weller et al. 2024 thermodynamic models, are available through MageMin. What I have done is I've written PetThermoTools so that when calculations occur, you can choose whether to run calculations with melts or whether you want to run calculations with one of these models available in MageMin. You don't really have to change anything about your calculation or about how you set up the calculation other than telling PetThermoTools which thermodynamic model do you want to do. If you say one of the melts models, it will send that information to alpha melts and perform melts-based minimization calculations. If you choose the Green or Weller thermodynamic models, it will send that information to MageMin and the minimization calculations will happen over there. Regardless, the results are then returned back to your main Python process and are formulated in a way so that the results actually have the same format as they come back to the main Python process, regardless of which bit of software you actually use to run those calculations. And a really important thing with this is, going back to the melting calculation example I showed a minute ago, we can basically run the same calculation using different thermodynamic models and then compare the results. So here is 2 simulations of mantle melting, one using the Green et al. 2025 thermodynamic model and one using the PMelts thermodynamic model. And you can see a couple of interesting features. Firstly, melting actually initiates at higher pressure for the Green et al. Model, but the kind of melting rate is actually higher once melting initiates for PMelts over here. So there's a couple of differences between the different model predictions. And to emphasize what I've done, all I did here was run a very similar model. So adiabatic decompression melting, bulk composition of the KLB1 peridotite, 1350 degrees Celsius mantle potential temperatures, starting around 30,000 bars, ending at 2,000 bars, with a pressure step of around 200 bars. Okay. The only thing that has changed between these two models is this parameter M. Okay. So in the first loop of this, in this loop here, the first iteration, M is going to be PMelts. So it's going to finish with this graph on the right-hand side. On the second iteration of this loop, M is going to be Green 2025. Okay. So this is showing that this one function, just by changing this one parameter, this model keyword argument, you can access the alpha melts software to run melts calculations, or you can access MageMin and run calculations with the alternative thermodynamic models. Comparing these different models is something that's really important, and until recently has really been done very, very rarely in the literature. It's incredibly important to compare these different models. You can see there's quite big differences here to understand what are the true uncertainties associated with thermodynamic modeling. Okay, there's a couple of things to finish up. We're going to go back to another example. So once again, we're running a crystallization model here. We're going to run this crystallization model at 4 different pressures. That's why I'm indicating with this arrow here, okay? So we're running 4 separate crystallization calculations in one function here. And one of the really important things with PetThermoTools, I kind of spoke earlier about the fact we have some inbuilt plotting tools, like Harker function that I mentioned earlier. Okay? But also, we've been really careful with how we design outputs to these calculations. And we did this because what it allows you to do is take those outputs and directly integrate them with other Python-based packages that have been designed for petrological research. Some of you may have come across Pennyweezer's PySolveSat package. We can directly take isobaric crystal, this function up here, and we can plug that into PySolveSat to calculate the sulfur content at sulfide saturation during these crystallization calculations. We can also take this output and plug it straight into Thermobar to plot up mineral compositions predicted during these crystallization calculations on things such as the pyroxene quadrilateral. And that kind of finishes what I wanted to talk about today. The 4 main things that we've been able to achieve through developing PetThermoTools. The first is providing wrappers, simple, easy to use functions for common thermodynamic calculations, primarily working initially with the alpha melts underlying source code, but then transitioning to also use the MageMin source code as well. The second thing we're able to achieve is greater stability in the calculations. The ability to run those calculations without having to worry about whether or not one of them is going to fail and terminate the rest of the calculations in your queue. That comes along with some speed benefits to the calculations as well. The third thing is the integration of MageMin, allowing us to compare the melts thermodynamic models with alternative thermodynamic models. And then the fourth thing is the integration with other Python toolkits, with PySolveSat, Thermobar being used as examples here. This basically means that now melts or MageMin calculations can be used as part of your Python workflow. You can use these, plot up the results, integrate the results with other kind of software packages in order to create a kind of more holistic approach to thermodynamic and petrological modeling. Hopefully you guys have found this useful. There are going to be far more videos going up, including installation instructions and also example calculations stretching a number of different things. We are going to be continuously updating the figure I showed earlier, showing what functions are available in PetThermoTools, so please do check out our read the docs for that. And if you do have any issues, there are definitely bugs left in the code. If something happens and you think it's not right, you're not getting calculation results, or something's gone wrong with installation, anything at all, please get in touch. I'd really like to know when things are going wrong so I can fix them, because it probably means that someone else is also having that issue. Thanks a lot for listening.